Hello everyone, my name is Mark, your teaching assistant for AAE451. Today we're going to talk about performing an aerodynamic analysis in XFLR 5. So I think everybody is familiar, at least heard of XFLR 5. I'm assuming that you have worked on this, used this software before doing your undergraduate curriculum, for example, AAE333 or 334, or you may have used it in one of your clubs that you've been involved with, but we're going to assume that, and we're going to assume that you are a beginner of the software, and we're going to walk you through starting with the basics. But before we started to dive into the software, and this is kind of what my experience of using this software, and I kind of created this kind of a workflow, the idea behind the software, how it works. So the approach of XFLR analysis is starting from 2D analysis, and you work your way up all the way to a 3D analysis. So for 2D, what does that mean? You're going to have an airfoil. You're going to import the airfoil into the software and define and refine its geometry. And then once you have the look of the airfoil, you're going to perform a 2D analysis, aka a polar. And then, so for that analysis, you can select a fixed Reynolds number or angle of attack, or you can select a multiple Reynolds number and angle of attack, and then that's called a batch analysis. And then once we have a good idea of all of the airfoils that we're going to use on our airplane, then we can move on to the wing and plane design in 3D, where we will define the plane geometry, the wing, the tail, and then the fin. But of course, you have a clean configuration, which is wing with no flap. Of course, you also need to know the aerodynamic analysis of the flap airfoil. So you need to go back and here to create not just the clean configuration, but also the dirty configuration. So once we know the geometry of the airplane, we're going to define its mass properties. But all of these locations of the masses are with respect to the wing's leading edge. So once we have defined what the plane will look like, we can start defining an aerodynamic analysis in 3D. And these are the list of options that you can define in the settings panel. We're going to talk about them later on as we get there. But just so you know that the polar types, you have different types of analysis. So fixed speed, you have fixed lift, and then you have fixed angle of attack. There's more. But today we're going to focus on the fixed lift analysis, assuming the plane is in 1G steady level flight, steady level unaccelerated flight. So, and then once you have the aerodynamic analysis ready, then you can move on to a stability analysis. And we are not going to cover them in detail today. There is going to be another video discussing this in way more detail. But the idea is that you must have your airfoil before you can perform an aerodynamic analysis, and then you must have an aerodynamic analysis before you can perform the stability analysis of your airplane. So with that said, we're going to move this to the bottom left corner. We're going to keep it here, and then. So this is the softwares, but before starting the project, I would like to show you this website. This is the XFLR 5 official website. Of course, this is where you can download the latest version of the XFLR, but it also has the documentation in here. So there's a lot of theoretical backgrounds of what the software is actually doing. If we tap in one of them, you can see that a lot of these things are familiar to you. You have seen them in your undergraduate curriculum, and then we're going to use some of this as our reference as we go. And then there's also some troubleshooting documentations for you in case you run into some error. So with that said, let's actually start using the software. So I have already created a new project right here. So if you just click on that, so new project, we're gonna hit no. So new project is a blank page. But if you go to the menu bar, I'm on a macOS computer, so all of my tools are located inside of here. So we're going to click on Module. We're going to click on Direct Foil Design, and then there's this folder icon. You're going to click on that, and then So we need to have an airfoil data ready. So for that, we are going to go to the Airfoil Tools website or the UIUC Airfoil database. So actually, Airfoil Tools is referencing the source data file of the NACA 2412 from the UIUC Airfoil database. So if you save this as a if you save this save the data file, which we will have here. So this is the file that we just downloaded. And then for Mac users, you need to remove the txt extension, but keep the .dat file. And I'm not sure about the Windows, but I'm assuming that it will be similar. You can try txt if you want. So we're going to import this file that we just downloaded into XFLR. So there's the NACA 2412 standard foil, used in Cessna 172 and many other aircraft, and also textbook as well. So once you open this, and if you zoom in, you will see that this airfoil is kind of jagged, right? Because we don't have a lot of data points to work with. So one thing we're going to immediately do is refine it. So we're going to click on the airfoil NACA 2412. We're going to right-click, and then we're going to refine globally. So I'm just going to jack it up all the way to 200. You can probably get away with probably something over like 100, 150. And then we're going to hit OK. And then we're going to replace the existing airfoil and hit yes. So this is the refined airfoil. And once we zoom in, you can see that the curvatures are a lot more smooth. So that's what we want. And of course, I want you to pay attention to, you can show the center line of the airfoil. You can style it if you want. We're not gonna touch that into here. Of course, you can see that these properties of the airfoil as well. And then you can right-click. Once, of course, we talked about that. We want to we also want to define let's say the flap, the elevator, the horizontal stabilizer, right? So if you want to create a flap, you can do that right here as well. So you can set the flap. Of course, you can set a trailing edge gap if you want to, of course, allow high pressure air flow over to the upper surface to promote, to delay flow separation, of course. And then you can set, so we're going to set flap. And you can set the leading edge flap, you can set a trailing edge flap, and then flap angle, and also you can define the XY position of the hinges, and then the chord and thickness. All of this is pretty self-explanatory. So we're not gonna do that for now. So that's the idea. So you can refine it. You can set flaps, and you can scale the camber and thickness if you want. Be careful with what you're doing. If you of course, read some of the documentations on how this actually performed. But so once we have the airfoil ready, so this is ready to go airfoil, so we're going to move on to module, and we're going to move on to direct analysis. So you might wonder, what is the XFoil inverse design? So the difference between inverse and direct design is that a direct analysis is that we have an airfoil that we know we have created. We want to know its aerodynamic properties. Whereas the inverse design is we are going to import a default airfoil, and then we're going to tweak and modify this airfoil to get the performance that we want. But this is a little bit tricky. I will be extra careful and be extra careful with this inverse design tool. You can look it up, some tutorials on YouTube. They have some explanation on that. But today we're going to focus on direct design, which we will use the most. So NACA 2412 shows up right here. We're going to So immediately we're going to do is we're going to go to the menu bar. We're going to go hit analysis. You can define analysis, but we're just going to batch analysis right here. So of course you can select if you have multiple airfoils, you can perform multiple analysis for multiple airfoils at the same time. And then this is where you can define your Reynolds number range. And then of course you can input your Mach number, and then your end critic is the it is settings that you can force the transition to turbulent. You can look it up on the internet for more details. And then polar type T1 is usually sufficient. And then this is another transition setting. So it's called forced transition, meaning, of course, XFLR will use its aerodynamic equations to calculate where the transition to turbulent flow is supposed to occur. But if let's say I set this top transition to 0.9, and the XFLR calculation shows that the flow has not become turbulent at 90% of the chord, then the forced transition setting will automatically force the flow become turbulent beyond 0.9 chord, 90% of the chord. Same thing for the bottom mount. So we're going to keep it to default of 1. And then analysis range is that you can specify a range of angle of attack, or you can specify a range of lift coefficients. And I would always start from the analysis. I would always start from 0. So that meaning the analysis will start from 0, go -1, -2, all the way to -10 per the increment, and then it will return from 0 and then start from 1 to 0.56 all the way to my max. And this is the increment that I have set. You can be a little more coarse or fine depending on what you want to do, but the range of the angle of attack should cover the useful range. So meaning, let's say if you want to perform a dive, so maybe -10 is a good idea, and then you want to know, and you of course you certainly want to cover beyond your maximum or critical angle of attack, right? So, and then we are going to initialize the boundary layer between the polars. Of course, we want to click on that. We want to store the operating points. This is very important so that for each angle of attack that you have specified in here, that you can locate that angle of attack on the, let's say, the drag polar or lift curve and all of that. You can pinpoint where that lift coefficient or drag polar value is. And then, of course, you're going to update the polar view. And then this setting is computer dependent. So I am on an 8-core CPU, so I'm going to use all of my available computing resources, and we're going to hit analyze. So yeah, so at the bottom you'll see analysis completed, and then we're going to close it. So we're going to full screen this software. So once you have performed an analysis, you will see this little arrow on the left, and then you can also see this little X over here. So this is where you can hide and show the polar analysis, and then you can, of course, you can define the style as you would for an airfoil. So we're going to hit this arrow, triangular arrow. So it will expand the analysis. So you can see that this is a T1 analysis. So you can see the polar type is T1, and then the Reynolds number, the list of Reynolds number that we have defined right here, this is a millions, and then this is your Mach number, this is your end critical value that I show here. And then again, you can hide them, show each individual if you wish. So we're going to hit hide all of them, and then we're going to open the first one, and then we're going to hit, and then we're going to hit just to see this individual polar curve. And then this is the operating point I was talking about. So this red square indicates this is the operating point at -10 degrees. And then as you move down, you can see that as you increase your angle of attack, your let's say your, do I have a, I don't think I have an angle of attack. So let's just say we're going to change this one to, oh, this is a good idea. So this is a good point to discuss the graph settings. So if you right-click on one of the curve polars, you can go to current graph and then define graph settings. So you can set the x-axis value and y-axis value. So in this case, if I'm interested in lift curve, so we're going to hit y-axis as lift coefficient and then x-axis as angle of attack. We'll hit OK. So this is my lift curve, right? So then as I move along the lift curve, I raise my angle of attack, my lift coefficient increase until a certain point, which I will stall. And then, of course, you can also see these useful information as here as well. So your Reynolds number, your angle of attack, your Mach number, and crit, your lift value, lift coefficient value, your drag coefficient value, your moment coefficient value. I don't know what CDP and then CPMN is, but this is the location of the critical point. So XCP, and then your top transition and your bottom transition. So this gives you a good idea. So let's of what the X-foil analysis will look like. Of course, and then over here, this is the lift, like the span-wise distribution of your analysis. So, for example, let's take a look at one of the flatter ones. So we'll enable this one, right? You can see that this is the lift pressure coefficient distribution along the x-axis for this airfoil 2412 at 0.25 degree angle of attack. So you can see that right here. And you can see that the top transition is at 85% of the core, and it's about right here, right? From some of your, you should know this from your AAE451 knowledge. And then, of course, we can do the same idea is we can, hold on a second, let me see, CP graph or the Q variable, I don't know what that is. Oh yeah, and also if you zoom in too far in or too far out, you can go to the current polar, and we can CP graph. We can reset graph scales, so it takes you back to the original scale. I believe you can also find the C coefficient of friction, but I have a hard time remembering where it is. But we're going to skip that for now. Of course, you can also have really useful information down below as well. And then you can see the pressure. You can animate that with respect to angle of attack. So this is very useful. So I'm going to show you my senior design, one of the XFLR project from my senior design. So we're going to save this, and we're going to say AAE451 S2024 XFLR Aerodynamics demo. So let me show you what my senior design aircraft will look like. So let's go to module, direct foil design, and then you can see that this is all of the airfoil that we have created analysis for, and I haven't shown all of them yet. And you can see that we have a clean airfoil, and we also have the different elevator deflection or flap deflection, and then we can move on to the direct analysis. You can see that this is all of the XFLR analysis that we have performed, right? So we have a cock Y, and then we have different flap settings. So you need to have all of these analysis ready before you can move on to the wing and plane design. So let's move on with my example right here. Move on with this example right here, spring 2024. So once you have all of the airfoils ready, so you can move on to the the last module, which is wing and plane design. So we're going to select this plane view right here, and then we're going to hit the menu bar plane. We're going to define a new plane, and this is the settings that you have right here. So you can give it a name, you can give it a description, but you can define the inertias right here. So main wing, elevator, and fin. You can create new items like batteries, propellers, I don't know. For an RC airplane, you probably have some servos, maybe your engines. All of that, you can create new entries and define them right here. And then, so you could just going to put in how much mass it is and how much the XYZ position with respect to the leading edge of your main wing. So we're going to hit save right here. But for the main wing, we can define, so this is your location. I would recommend keeping this as 0, 0. And then tilt angle is your wing instance angle of your main wing. And of course, if you're interested, you can choose a biplane design. And then you can also define your, this is where you can define your elevator. So your XZ location, and then your tilt angle is the elevator, horizontal stabilizer incidence angle. Even though it says elevator, is really the incidence angle of the horizontal stabilizer. You can do the fin here as well. You can have two-sided fin, or you can choose double fin, but we're going to keep it simple as one fin right here. Of course, if you want, you can also create incidence angle of your vertical stabilizers as well. So let's start with defining the main wing. So, so this is your first section, highlighted in red, and then this is your second section, highlighted over here. And then you have the chord. So chord is about 7 inches right here, or 7 unit, and then 4 over here. And then you have an offset, which is swept wing. So we have about like 2.7 degrees of swept from here to here. And then dihedral, it's 0, but if we can set it to, let's say, something like 2 degrees, you can see that the wing is raised up. You can also set your wing twist to mimic better elliptical wing distribution. And this is where you can select your airfoil, right? So we only have one NACA airfoil analysis, so this is the only one we can choose. And then the X panels and X distance and Y panels or Y distance are the the analogy is similar to like a CFD mesh grid. That the higher the number right here, the finer the mesh grid will look like will be. And then for more details, you can go to the XFLR analysis, XFLR website, and then you can find some theoretical background. You can find that the lifting line theories that it's using, and then the VLM methods, the vortex lattice method, and then there are different VLM methods available in the software, but VLM2 is usually a better one. So yeah, you can look it up in more details if you want to. But yeah, so we're not going to save this. Oh, well, we'll save it anyway. Of course, you can enable to see what the panel will actually look like right here. You can look at the foil names. You can choose different airfoils for each section. So this will be particularly useful when you're trying to create flaps on your wing, or you want to create elevator, rudder, or aileron deflections on your airplane. The masses, we're going to worry about that right now. Of course, different view settings, and this is sort of the specs, right? The specs of your main wing. So all of the geometry, and then your VLM panels, all of this right here. So we'll hit save, and then we'll hit save as well. Of course, you can see the plane level geometric informations are right here. And again, you need to define your plane inertia. But one thing I want to mention really quickly is that these are the the inertia points that you have defined in the plane inertia setting. So the bigger the sphere, the heavier it is, and then the location. If you have defined the location of the inertia, it will be displayed somewhere along this coordinate axis. And then I don't really recommend people to install to define like the fuselage of the airplane inside of here, because it's not recommended by software. So again, you can refer to the official website on explanation on why this is the case. So we'll hit save. But let's go ahead and take a look at my senior design aircraft. So this is what it looks like, and then we can edit the airplane so you can see that we have a wing instance angle. We didn't have any elevator instance, horizontal stabilizer instance angle, because the airfoil is a clockwise, which is a cambered airfoil but inverted. Don't save. And then we can see the inertias right here. Of course, I'm assuming your guys' airplane will be a little bit more detailed than mine. And then we'll hit save. And then the main wing, we can define them right here. So you can see that the airplane has flaps, right? So there's a middle section that we cannot implement flaps, and there's an outer section that we intentionally do not use flaps because we want to avoid tip stall of the airplane. And again, this is where you can implement different airfoil geometries. And then of course you can unclick the symmetric section. So this will be great if you want to perform, let's say, an aileron roll to see what the plane will behave. But since this is a landing configuration, we're just assuming to be specific. Of course, once you deselect symmetric, right side, left side will be separate. So we'll hit save, and then we'll hit save. So yeah, this is what the plane will look like. And then, so once you have finished, so we'll start with this one. This is the 0 flaps, so this is the clean configuration. I'll make it a little bit bigger, right? This is the clean configuration, and this is the dirty configuration. Yeah, hope this is a better view, right? And then once we have defined the inertia and the geometry of the airplane, we're going to move on to the plane analysis. So go to analysis, and you define an analysis. And then this is the analysis definition panel, right? So as we discussed before, you have type 1, type 2, type 4, and type 5. So fixed angle of attack, fixed lift, fixed speed, and then beta range. Beta is the side slip angle of the airplane. So we're going to assume type 2, and then we'll hit the analysis, right? We'll use the ring vortex vortex lattice method, VLM2, and we're going to select the viscous settings, so to include induced drag. Of course, these things are not recommended, so don't click on that. And then inertia, right? You should use the plane inertia that you have defined from the plane definition. So always, most of the time, you should click on use plane inertia. And the reference dimensions is the XFLR documentation recommends selecting the wing planform projected on the XY plane, so we'll follow their recommendations. And then the aero data is where you can define your the property of your air, of the air the airplane is flying through. So you can select to be standard atmospheric conditions at sea level, but you can change that if you want for your liking. Extra drag. So one thing I would like to mention is that even with viscous analysis enabled, XFLR still hugely underestimates the drag of the airplane because the missing of the fuselage. So if you have a drag buildup analysis that you want to incorporate into the analysis, this is the place you can put it. Okay, you can have extra drag, extra area, extra drag coefficient. So we don't have any of that. We're going to assume there isn't. So we're going to hit save. Then we're going to hit T2 indicates this is aerodynamic analysis, and then VLM2 is the panel method that we're going to use, right? We're not going to use lifting line theories. We're going to use vortex lattice method, and then this is the second option. And we'll hit demo. We'll hit OK. So yeah, so you can see the plane analysis panel right here, just like 2D foil analysis. You will have different alpha ranges, and then the delta is the increment between these ranges. Of course, we always select the store operating points, and then we'll hit, and then we'll reset the scale, and then we'll make it look nice, and then we'll hit analyze. And then again, so this is the result of the 3D panel analysis. Of course, because we have such a wide range of angle of attack selection, and the software are just going to assume, and it's just going to compute it. So in some cases, it will not converge. It's okay as long as we get some valid results out of it. So again, you can move down along the angle of attack and see the plane change, the plane's behavior changes. So we're going to click on some of the graphical displays. So you can see we enable some surfaces and then masses, right? This is the masses of my senior design team have defined, and then we can click on foil names. So, and again, you can see the behavior of the plane as you increase and decrease the angle of attack. And then you can also choose to animate that if you want. And then, of course, these are also very useful information located at the bottom left, the corner right here, the bottom right corners. We're not going to repeat that, but this is where you can find some, so these information will be very useful for your analysis. So we will also move on to this setting right here. So that's called operating point view. So this is the span view of your aircraft. So think about you're looking at the airplane straight on or from the back of the airplane. So this is the span distribution, so negative 50% to positive 50%, and then this is the metrics that you're looking at. So in this case, we are looking at the lift coefficient distribution along the aircraft, and then as you move, so this is a fairly elliptical distribution for the main wing, and this is going downward is because we have a vertical tail that's producing lift negative drag. Again, you can choose different graph settings. If you want, you can look at induced angle of attack. You can also look at some moment coefficient, I believe. I don't remember where exactly. Oh, bending moment, there it is. So this is the bending moment, right? Of course, it will be the greatest at the root. So this is a useful graph analysis. And then we can move on to over here. This is your polar view, like you would see on plane analysis. Sorry, 2D analysis, right? We have a lift curve right here. We have, let's say we can create a drag polar if we want. So current graph, define graph settings, and then CD versus CL, we'll hit OK, right? So this is the lift curve of the airplane. Again, if you move along the operating point, the little red square will move. And then, of course, as you increase your angle of attack, the lift coefficient will increase, and then because your drag is increasing, the horizontal speed will decrease, right? You can see that from the second graph over here. So right, we'll increase the angle of attack. The airplane will slow down at the same altitude. So at this point, right about this point, right? So about angle of attack of 4.5-ish, that the plane has 0 moment coefficient. That means it's not going to pitch up and pitch down. And we are at a very small, almost negligible, also that's verified right here. And then that tells us that at the angle of attack about 4.5, the airplane will be level, flying around 21 feet per second. And then angle of attack about 0.85, and then drag coefficient about 0.06. Of course, this is not going to be a reasonable drag coefficient. Because we are underestimating drag tremendously. So this is pretty much everything about. Of course, you can look at the same distribution, CP distribution along the aircraft as you would on the foil analysis. So so this is pretty everything that you need for the you need to know about basics of the aerodynamic analysis inside of XFLR. Of course, we will have another. Of course, there are some limited analysis in terms of aircraft stability that's also involved in here, but we're going to talk way more about stability and control in a separate video. So that's it for me today, and thank you very much.